Hi all. So in last class we discussed Stokes theorem and some of the problems from Stokes theorem. So far we have discussed line integral and surface integral. So today we are going to discuss volume integral and one of the theorem from volume integral. So that is divergence theorem or Gauss-divergence theorem. Okay, so first we can see what is volume integral. So already we discussed the line integral, that is single integration, and surface integral, that is double integration. So in volume integral, so there will be three integration. So you already studied the triple integral. So in last semester. So here we will discuss the volume integral over a vector field. Okay, so we are extending out to a vector field. So in this class we will discuss volume integral over a vector field. Consider a vector field f. Consider let vector f is equal to f1i plus f2j plus f3k. So here f1, f2, f3 are functions of the variables x, y and z. So f1, f2, f3 are three variable functions. They are functions of x, y and z. So then the volume integral is given by the volume integral of vector f over the given region E, and that region is enclosed by the surface S, and that is given by, so I will notate it by using three integrations. So triple integral of vector f dv over the given region E, and the region is enclosed by the surface S, and simply you will integrate it like this: vector I into triple integral of f1 with respect to dv over the region E plus vector j triple integral of f2 dv over the region E plus k vector into triple integral of f3 dv over the region E. So here dv is nothing but dx, dy, dz in any order. So here order doesn't matter, so you can change the order. This can be either dy, dx, dz or dz, dy, dx, or in any order. There will be 6 different orders: dy, dz, dx, or dz, dx, dy, or dx, dz, dy. So like this, in any order you can use, so that is up to you. So just triple integration. So, and we know that we will do the inner integral first, then we will move to the outer integral. Okay, so the same integration process, and you will see how to integrate over a volume integral. Volume integral for finding the limits of these variables x, y and z. So the same process which we discussed in last semester we will use here also, and only difference is here we have a vector field f. Okay, that we'll discuss in problem. Now we'll move to the theorem, that is Gauss-divergence theorem. The theorem says that if vector f is a continuously differentiable vector function in the region E, and the region is bounded by the closed surface S, then that Gauss-divergence theorem tells the relation connecting double integral and triple integral, and that relation is the surface integral of the vector field f is equal to triple integral of, or the volume integral of divergence of the vector field. So this clearly tells the relation connecting the surface integral and volume integration. Surface integral of the vector f, that is double integral f dot n ds, is equal to the volume integral, that is triple integral divergence of f dv. So here the div f is the divergence of f, and what is the divergence of a vector field? We know that divergence of f is equal to del dot f. Okay, divergence is del dot f. Okay. So this is called what? Gauss divergence theorem. This is called a Gauss divergence theorem. Okay. This tells the relation connecting surface integral and the volume integration. So here we may have a closed surface. Closed surface is, for example, one of the closed surface is the sphere. The sphere is a sphere is a surface. We know that is the ball shape. So sphere is a closed surface. So and the inside portion of sphere will give the region E. Okay, the surface is S, then the inside portion of the sphere is a given region. Okay, or for example, suppose we have a cube. Suppose we have a cube like this. So consider this cube. So we know that there are 6 faces for this cube, and it is closed. Suppose it is closed cube, and the inside portion of this cube is the region E, and the outer surface, the cubical surface, is our S. Okay, the surface S has 6 faces. S has 6 faces. Okay, so this is also a closed surface. Okay, these are closed surface, and the inside portion is E. Okay, and Gauss divergence theorem tells the connection between the surface S and the inside portion of the closed surface S. Okay, so we'll discuss some questions regarding this Gauss divergence theorem. So here is a question: verify divergence theorem. Divergence theorem is Gauss divergence theorem for the vector field f is equal to vector f is equal to x square minus yz I plus y square minus xj plus z square minus xyk taken over the rectangular parallel pipe 0 less than or equal to x less than or equal to a, 0 less than or equal to y less than or equal to b, and 0 less than or equal to z less than or equal to c. So rectangular parallel pipe means it is a portion like this. So it is not, if a equal to b equal to c, we will get a cube. If a equal to b equal to c, we will get a cube. So it is a brick like shape. It is a brick like shape. First we can identify the shape. So it is like this. So this is a shape of a rectangular parallel pipe. Given rectangular parallel pipe. Suppose if we consider xyz axis like this. Suppose this is your z axis, and this is your y axis, and this is your x axis. This will be our origin. This will be our origin. Oh, suppose this is xyz axis. This is a given rectangular parallel pipe at a distance 0 less than or equal to x less than or equal to a. So this distance is a distance, and this point will be a 0 0 0. This distance is a, and this distance origin to this point, this will be this point will be 0 b 0 on y axis, and this distance is b, and this point will be 0 0 c. Okay, at a distance. So since 0 less than or equal to z less than or equal to c. Okay, or otherwise simply here you will get 6 equations of surfaces. So from 0 less than or equal to x less than or equal to a, what you will get? You will get what? 0 less than or equal to x less than or equal to a, So from here you will get x equal to 0 and x equal to a. X is bounded between 0 and a. So x equal to 0 is an equation, x equal to a is an equation. What is x equal to 0? So it is a yz. X equal to 0 is yz plane. So you will get that yz plane here. Okay. And x equal to a is the portion of that portion is this one. This rectangular portion you will get. So like that, two planes you will get. Similarly, if we consider 0 less than or equal to y less than or equal to b, you will get y equal to 0 and y equal to b, another two plane. If you consider 0 less than or equal to z less than or equal to c, you will get another two planes, z equal to 0 and z equal to c. But here we don't want these things, so we can directly go to the problems. The correct method is first is this one. Correct method is this one. So first you need to identify the given planes and you need to draw the planes. Then you will get a surface, closed surface and a bounded region. So here what is the closed surface? Closed surface is the surfaces of this rectangular parallelepiped. There are 6 faces. There are 6 faces and the equation of that faces we got here. Okay, there are 6 faces and the inside portion of this rectangular surface is E. The inside portion of this rectangular surface is our E. Okay, this is inside portion is E. So the question is to verify Gauss-divergence theorem. So verify Gauss-divergence theorem means what? So you need to separately find out the left hand side and the right hand side of the Gauss-divergence theorem. So here we have the Gauss-divergence theorem. Double integral f dot n ds is equal to triple integral over the region E, divergence of f d. So we are going to find out the left hand side of the Gauss-divergence theorem. So that is double integral f dot n ds. So that we can find. So first write down the. So what we need to find? We need to find double integral f dot n ds over the surface. Yes. So the surface is the closed surface. That is the portion of the rectangular parallelepiped. So here this rectangular parallelepiped is not a it is not a smooth surface. So we can see that. So there are many corner portions and at the corners it is not a smooth. So we know that at corners the surface is not a. So we need to divide this into smooth surfaces. So if you look at the rectangular parallelepiped, you will get 6 planes, right? So it is a combination of 6 plane surfaces. So you will get 6 smooth surfaces here. So what are all the 6 smooth surfaces? If you consider this as A, B, C, D, and this is O, P, Q, R. So you can divide the surface into 6 smooth surfaces. Consider S1 is nothing but A, B, C, D. So what is the equation of that surface A, B, C, D? So you know that it is the equation of the surface x equal to A. So equation of the surface is x equal to A. X equal to A is the equation of that surface. Okay. So what is S2? S2 we can take it as the plane O, P, Q, R. So O, P, Q, R is YZ plane. So YZ plane, equation of YZ plane is this one, x equal to 0. X equal to 0 is the equation of YZ plane. Similarly, S3 you can consider B, C, Q, P. Okay. B, C, Q, P. So it is the plane parallel to XZ plane, this plane, right? And what is the equation of that plane? It is y is equal to b. Similarly, S4 you can consider A, O, R, D. So it is a XZ plane. What is the equation on XZ plane? It is y is equal to 0. Similarly, 2 more planes. S5 we can consider S5 as what are remaining two planes. We can consider CDRQ. So CDRQ, plane CDRQ. It is a plane parallel to XY plane. So that is this plane. The equation is Z is equal to C. So I'll get a Z is equal to C is the equation. Similarly, another one, S6. It is a plane on XY plane, that is ABPO. Equation is Z is equal to 0. So like this we have 6 smooth surfaces. So instead of finding the double integral f dot n ds over this S, you can just find out double integral over S1 f dot n ds plus double integral over S2 f dot n ds plus double integral over S3 f dot n ds plus double integral over S4 f dot n ds plus double integral over S5 f dot n ds plus double integral over S6 f dot n ds. Here f is same. F vector is the given vector field, but here n is changing. N vector is the unit normal vector to the surfaces, but here unit normal vector is changing over S1, S2, S3, S4, S5 and S6. So separately find out, you can notate it as N1, this is N2, this is N3, this is N4, N5 and N6. Separately give the name. Now you can separately find out this this surface integral. So put it as equation number 1. So over S1, so what is S1? S1 is ABCD. ABCD is the surface, plane surface parallel to YZ plane. So to YZ plane, what is the unit normal vector? Unit normal vector on x direction. On x direction, unit normal vector is what? It is nothing but I vector. On x axis, unit normal vector is I vector. Similarly, what is S2? S2 is x equal to 0, that is YZ plane. So there, unit normal vector is to the opposite direction of x axis. To the opposite direction of x axis, it is at the back side, right? That plane is plane OPQR is at the back side. So the unit normal vector is to the opposite side of x axis, that is negative side of x axis. So that unit normal vector will be minus I vector. Clear? Similarly, y equal to b. So over S3, y equal to b. So we'll get a unit normal vector through y axis, that is j vector, and the similar process you'll get it n4 is equal to what? Minus j vector, and here you'll get n5 vector, so that will be k vector, and n6 vector you'll get a minus k. Okay, now we can separately find out what double integral over S1 f dot n1. What is n1? N1 is I vector dot ds. So ds is if here you can see that it is a plane parallel to YZ axis. So plane parallel to YZ plane. So what is ds actually? For finding ds, we need to project it onto any of the surface. So here it is since it is parallel to YZ plane, we can project it onto what? YZ plane. So project it onto YZ plane. Project ABCD onto YZ plane. So here you can write this is ds is instead of ds. So what you will get? F dot I. F vector is, what is F vector? F vector is equal to x square minus yz I plus y square minus xz j plus z square minus xy k. So if you take the dot product with I vector, you will get only the I component, that is x square minus yz. Okay, right? And ds is nothing but since you are projecting onto yz plane, it is dy dz divided by magnitude of n dot k. Here n vector is, what is n vector? N vector is nothing but I vector. So n dot unit normal vector to yz plane, that is also I vector. You will get I dot I is equal to 1 only. So what is ds? ds is dy dz over magnitude of n dot the unit normal vector to yz plane, that is I vector. Okay, and substitute n vector is I vector. So you will get that. So I dot I is equal to 1. Now, so you need to find out the limits of y and z. So what is the limit of y and z, and what is x? So over x, that is over the surface S1, x is equal to a, that you can substitute here. So you'll get a square minus y into z, right? dy dz. And the limit of y, what is the limit of y over the surface x equal to a here? So this is the surface x equal to a, and y is varies from where to where? 0 to b, and z is varies from 0 to c. So that is given in the question. So 0 to b and 0 to c. ABC are given generally, so no issues. Now do the inner integration. Integral path is simple. So integral of a square is a square into y, integration with respect to y, right? And integral of y is y square by 2, and z is cos from 0 to b dz. Now we will put the upper limit and the lower limit is 0. So if you put the upper limit for y, you will get a square b minus b square z by 2. If we put lower limit, it is 0. Now integrate with respect to z. A square b is constant. Integral of a square b is a square b z minus b square 2 by 2 is constant. Integral of z is z square by 2. So you'll get z square by 2 into 2 is 4 from 0 to c. Now we'll put upper limit for z. So a square b c minus b square c square by 4. If you put the lower limit, it will be is equal to 0. So this is our S1. Similarly, we can find out our S2. So what will get S2? S2 is the surface x equal to 0, right? So our S2 f dot n d S2. So what it is actually? Double integral over S2 f dot. What is the n2 vector? N2 vector is already we found. N2 vector is minus I cap. So here also you will get the I component of f vector only, that is x square minus yz. But since minus I is there, so negative of x square minus yz will get. And ds2, it is the same dy dz by. So what is ds2 or s2? It is dy. So since it is on yz plane, so that surface S2 is R, Q, P, or otherwise O, P, Q, R. It is on yz plane. Equation of yz plane is x equal to 0. That already we are written x equal to 0. So since it is on yz plane, so we are integrating over with respect to y and z. So no need to project, it is already there. So it is dy dz over magnitude of n dot the unit normal vector to yz plane is I vector. And n vector is also minus I. So we'll get minus 1 there. Since it is modulus, since we are taking modulus, here we'll get minus 1. So since we are taking modulus, you'll get dy dz only. So this is actually dy dz only. Okay. So or otherwise you can write it over minus 1, magnitude of minus 1. So that will get plus 1 only. Okay. Now this is nothing but, so what is the limit? Limit of y is 0 to b, limit of z is 0 to c, that minus we are taken outside. What is x value? So over s2, what is the equation of s2? It is x equal to 0. So since it is x equal to 0, that will not be there. We will get minus yz dy dz. So this minus and minus will become plus. So here we will get integral 0 to c, integral with respect to y, that is y square by 2z, from the limit 0 to b dz. So now we will put the limit for what? Limit for y 0 to c. If we give the upper limit, we will get b square by 2z. If we put the lower limit, it will become 0. Now integrate with respect to z. B square by 2 is constant. We have taken it outside. Integral of z is z square by 2 from the limit 0 to c. So put the limits. We will get b square, c square by 2 into 2 is 4. If we put the lower limit, it will become 0. Now this is a surface integral over surface S2. Similarly, you can find out surface integral over S3, S4, S5, S6. That will be analogous. Analogously, you will get the answer. So that will be double integral over S3 f dot n3 ds3 will be is equal to. So you will get like this: double integral over s3 f dot n3 ds3 is ab square c minus a square c square by 4, and double integral over s4 is a square c square by 4. Double integral over s5 is ab c square minus ab a square b square by 4, and double integral over s6 is a square b square by 4. So like that, like this, you will get the answer. You can just check. The process is same. Therefore, I am not doing it again and again, but you have to do it. So therefore, what is the total double integral? So I guess number 1 implies, you can write here, 1 implies double integral over s f dot n ds will be is equal to, just add up all the double integration. So that is a square bc minus a square, minus b square c square by 4, right? Over s2 it is b square c square by 4. So plus b square c square by 4. Next over s3, ab square c minus a square c square by 4 over s4 plus a square c square by 4 over s5. It is ab c square minus a square b square by 4 and over s6. It is a square b square by 4. So here you can see minus b square c square by 4 plus c square b square c square by 4, and this thing will cancel. So what remains? A square bc plus ab square c plus ab c square. See here in all the terms abc is same, common, so you can take it outside. What remains inside? A plus b plus c. So abc into a plus b plus c, you get the total surface integral. So if you give some numbers, abc are generally given, so you can choose any number. If a equal to 2, b 3, c 4, you will get a particular answer like that. Okay, so this is the left hand side of the Gauss-divergence theorem. This is the left hand side. So similarly, we have to find out the right hand side. So what is the right hand side of the Gauss-divergence theorem? Triple integral divergence of f dv. For that, first we need to so divergence of f. What is divergence of f? It is del dot f. So what will get? It is nothing but dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. So by the equation. So that is dou by dou x of what is f1, f2, f3, f1, f2, f3 are this. So this is your f1, this is your f2, this is our f3. So substitute here and just find out the partial derivative. Dou by dou x square minus yz plus dou by dou y of y square minus xz plus dou by dou z of z square minus xy. So partial derivative with respect to x of this thing, partial derivative x square is 2x. Partial derivative yz is 0 because it is constant. Here partial derivative y square with respect to y, it is 2y. The remaining thing will become 0. So here we'll get 2z. So in other words, 2 into x plus y plus z. So this is divergence, but we need the triple integral divergence of f dv or the given region E. So this you can write substitute divergence 2 into x plus y plus z. dv you can write in any order. So suppose I am writing dz dy dx order. So if you are in here, we are integrating first with respect to z. So what is the limit of z, y and z? It is and x. It is given in the question. X is varies from 0 to a, y is varies from 0 to b, z is varies from 0 to b. Since it is parallel pipe, it is very simple to identify the limits. Otherwise, we have to do a limit of z is 0 to c, limit of y is 0 to b, limit of x is 0 to a. Now first we will integrate with respect to z. So take the constant 2 outside. Integral of x with respect to z is x into z. Integral of y is also y into z. Integral of z is z square by 2 from the limit 0 to c. dy dx. Put upper limit and lower limit. So 2 into integral from 0 to a, integral from 0 to b. Upper limit is z, so we'll get x into c plus y into c plus c square by 2. If you put the lower limit, everything will become 0. So no need to write it again. Now we will integrate this one with respect to y. So integral of xc. So that is equal to 2 into integral from 0 to a. Integral of x into c is c you can write. So integration with respect to y, therefore cx into y. Integral of y is y square by 2 into c is there. So c into y square by 2 plus c square by 2 is a constant. Integration with respect to y will be y c square by 2 into y. So limit is from 0 to b dx. Now we'll put the upper limit and lower limit for y. So we'll get cx into b plus cb square by 2 plus c square b by 2. If you put the lower limit, everything will become 0. So no need to put again. Now we'll integrate with respect to x. So bc is constant. Integral of x is x square by 2 plus cb square by 2 is constant. So this is actually integration with respect to x. We'll add 1x here also. 1x from 0 to a. Now we'll put upper limit and lower limit. So we'll get bc a square by 2 plus cb square a by 2 plus c square ba by 2. If we put the lower limit, everything will become 0. We can cancel these two by taking 1 by 2 outside. So now we can see ABC is constant. Sorry, ABC is common for all the times. So we can take it outside. What remains here? A. Here B remains. Here C remains. So this is the same as the left hand side of the theorem. So hence we can say that the theorem verified. Which theorem? Gauss-divergence theorem verified. So like this we can verify a theorem. For verifying divergence theorem, what we will do? So we have to separately find out the left hand side, that is surface integral, and the right hand side separately, and you need to prove both are the same. You need to verify both are the same. Here you can say that for finding the left hand side, it is a very lengthy process. So you need to evaluate the 6 surface integrals. But for finding the right hand side, it was very simple. By finding the divergence and this triple integral, you will get the answer. So in such cases, we can use the divergence theorem. So for finding the complicated surface integral, we can use the divergence theorem and you will get the answer easily. So for that, we will use this divergence theorem for simplifying the method of solving the question. Okay. Now we'll see one of the application of Gauss-divergence theorem for finding surface integral. Consider this question. Evaluate integral s f dot ds, which means surface integral. This is another notation for surface integral. only one integral is written there, but it actually means the surface integral because it is our s. So integral our s f dot ds that is to find surface integral where vector field f is given for xi minus 2y square j plus s square k, and the surface s is given. It is bounded by x square plus y square equal to 4, z equal to 4, and z equal to 0, and z equal to 3. So here some three planes are given, and the region is bounded by this closed surface. First thing, you need to identify the given surface. So x square plus y square is equal to 4. What is actually? So suppose this is x-axis, this is y-axis, and suppose this is z-axis. X square plus y square is equal to 4. We have seen this x square plus y square is equal to 2 square. So if only in 2 dimension it is a circle, right? Circle with a center at the origin and a radius 2. That is, if we consider only xy plane, it is a circle on xy plane, right? It is a circle on xy plane like this. It is a circle on xy plane like this, right? X square plus y square is equal to 4 with radius 2. So this point is actually 0 to 0, and this point is 2 0 0. But it is a surface in 3D space. So x square plus y square equal to 4, which means z can be anything. It is nothing saying about z. So z varies from minus infinity to plus infinity. So if you vary z, you will get many circles. So when z equal to 1, you will get a circle here, and if z equal to 2, you will get circle here. So like that. So if z equal to 1, you will get circle here. If z equal to 2, you will get circle here. Like that. Yeah, as z varies, you will get many circles. In between, there are many circles. So like that. If you combine all these circles, what you'll get? You'll get a cylinder. So it is actually a cylindrical portion. The portion of a cylinder. Okay. So this is the required sub x square plus y square is equal to 4 in 3D space. It is a cylinder with the axis on z axis. Okay. And it is given that it is also bounded by z equal to 0. Z equal to 0 means xy plane. So the cylinder is up to here only. So up to this z equal to 0. Okay. And z equal to 3. Suppose this is the point 3. So it is bounded by this z equal to 3 also. The cylinder from z equal to 0 to z equal to 3. Z equal to 3. What is z equal to 3? Z equal to 3 is a plane passing through the point 3, and it is parallel to xy plane. So that plane will be here. Okay. The plane will be here. So it is bounded by, the cylinder is bounded by z equal to 0 and z equal to 3. So you need to find out the single integration. So instead of finding the single integral, you can use the Gauss-divergence theorem. So you can just write by divergence theorem, integral s f dot ds, which is equal to, by divergence theorem, what it is? Triple integral divergence of f dv over the region E. E is the inside portion. So here it is cylindrical portion. So what is divergence actually? So you can just write down the divergence. So it is triple integral. So you can just find out the div f. Div f is equal to del dot f. That is, what is f vector here? F vector is for xi minus 2y square j plus s square k. So it is dou by dou x of coefficient of y, here it is for x plus dou by dou y of coefficient of y is minus 2y square plus dou by dou z of coefficient of k is z square. So what will get? Derivative for x is with respect to x is 4, plus derivative of minus 2y square is minus 4y. Derivative of z square is 2z. Oh, no, that we can substitute here for minus 4y plus 2z. dv is dz dy dx. In any order we can write, that is up to you over the region. Now we need the limits. So how to identify the limits? What is the limit of z? So here it is given that z is varies from 0 to 3, that you can write directly. Now what is the limit of y? So for finding limit of y, the actually in triple integration, how to find the limits? So for finding the limits, we'll consider a rectangular parallelepiped through the region. Consider a rectangular parallelepiped. So I'll change the color. Consider a rectangular parallelepiped through the region. That is, consider a rectangular portion. Consider a rectangular portion inside the region. So this is that region. Okay, consider a small region like this. Okay, so and for the z limit, what we'll do? Look at the lower side of the rectangular parallelepiped. What is z value there? It is 0. For the upper limit, look at the upper side. It is equal to z is equal to what? 3, right? Z is equal to 3. So the limit of z is from 0 to 3. And for the limit of y and x, other two variables, what we will do? We'll project it onto xy plane. Project onto xy plane. Project this region onto xy. If we project it onto xy plane, what will get? Projection onto xy plane. What will get? We will get this circular portion, right? On xy plane, what will get? Suppose this is y-axis and this is x-axis. We will get a circular portion like this. We will get a circle like this. Actually, we will get a circular region. So you will get a disc. Okay, disc. So we will get a circle. The inside portion of the circle will get. So this disc you will get. Okay. So this point is 2. This point is also 2. The equation of the circle is, we know that x square plus y square is equal to 4. Okay. Now, so we need to find out the identify the limit of y. So in two variable, we know that how to identify the limit of one variable. We'll consider a straight parallel to that axis. So here, since we are integrating with respect to y, so we'll consider a straight parallel to y-axis through the region. So we'll consider straight parallel to y-axis through the region. In 3 dimension, we consider a rectangular parallelepiped. There we got the limit of z. Now we don't want z. We projected onto xy plane. Now we need the limits of y and x only. So since we are here, we are integrating with respect to y first. We'll consider straight parallel to y. So what is y value there? It is a part of the circle. X square plus y square is equal to 4. So we need a y value. So y square is equal to 4 minus x square. So y is equal to under root plus or minus under root 4 minus x square. So since it is negative side of y-axis, this value will be negative 4 minus x square. And what is the upper limit? Upper limit will give y value here. Since it is positive side of y-axis, under root positive under root 4 minus x square. So that is the lower limit and the upper limit. Lower limit is minus under root 4 minus x square. Upper limit is plus under root 4 minus x square. Now we need the limit of x variable. It is varies from the least value and the largest value of x. So here it is minus 2. Here it is plus 2. So it is x is varies from minus 2 to plus 2. Now only integral part is there. So first we need to integrate with respect to z variable. So integrate with respect to z. Integral of 4 is 4z. Integral of 4y is 4yz. Integral of z square is z square by 2 from the limit 0 to 3 dy dx. Put the upper limit and lower limit. What will get? We'll get this is equal to minus 2 to 2 integral minus under root 4 minus x square plus under root 4 minus x square. We put the limit, upper limit, you will get 4 into 3 12 minus 12y plus 2 and 2 cancelled. 3 square is 9 dy dz. So this is nothing but integral minus 2 to 2 integral minus under root 4 minus x square to plus under root 4 minus x square 12 plus 9 is 21 minus 12y dy dx. Now we need to integrate with respect to y. Right? Now we need to integrate with respect to y. So integral of 21 is 21y. So this implies integral minus 2 to 2, integral minus under root 4 minus x square to plus under root 4 minus x square. Integral of 21 is 21y minus integral of 12y is 12 into y square by 2 with respect to y, right? So from the limit minus under root 4 minus x square to plus under root 4 minus x square. So no need to write that here. Already we written there, no? So we don't want this here. Okay. So now dx is remaining. Now we'll put upper limit and lower limit. What will get? So when you are putting upper limit, you will get 21 under root 4 minus x square minus 2 and 2 cancels. Only 6 remains. So y square. So under root 4 minus x square all square is 4 minus x square only. Minus the lower limit. So one more minus is there. So you'll get 21 minus under root 4 minus x square minus 6. So if you take the square, you will get the same 4 minus x square dx. Okay. Now this cancels. Minus 6 4 minus x square and this one, because minus into minus will become plus. And I will get minus 2 to 2. 21 under root 4 minus x square. Here this minus into minus plus 21. 21 plus 21. 42 under root 4 minus x square is there into dx. So here for solving this, it is better to give one substitution. So this is 422. You can write it as 2 times integral from 0 to 2 under root 4 minus x square dx. So here just give a substitution. Here put. So since for removing that under root, we can give x is equal to 2 sin theta or 2 cos theta. That is up to you. Suppose 2 sin theta. So whenever we are changing a variable, we have to change the derivative also. What is dx then? Dx is equal to derivative sin theta is cos theta d theta. So we need to change the limit also. When x is equal to 0, what is theta? X is equal to 0, you will get 0 equal to 2 sin theta from this equation. So this implies sin theta is equal to 0. So when sin theta equal to 0, when theta is equal to 0. So theta is also 0. So when x is equal to 2, we will get 2 is equal to 2 sin theta. This implies sin theta is equal to 1. So sin pi by 2 is 1. So that we know. So theta is equal to pi by 2. So theta varies from 0 to pi by 2. So this 2 can be written as that is the surface integral f dot n ds, or the surface s is equal to 42 into 2, that is 84, and integral from 0 to pi by 2 under root 4 minus x square, that will become under root 4 minus 2 sin theta square. So 2 square sin square theta, and dx is nothing but 2 cos theta d theta. 2 cos theta d theta. So 84 into 2 will get integral from 0 to pi by 2. So here you can take 4 outside, that is under root 4 you can take outside. It is common, right? So what is remaining? 1 minus sin square theta. What is 1 minus sin square theta? So we know that cos square theta plus sin square theta is equal to 1. So 1 minus sin square theta is cos square theta. So 1 minus sin square theta is cos square theta. So that you can substitute. Under root 4 is 2. So again that 2 you can take outside. So 84 into 4 integral from 0 to pi by 2. So this will become cos square theta under root. So it will become cos theta only. Cos theta into cos theta d theta. Now what is 84 into 4? No need to do. So we can cancel something. So here it is cos square theta, but we can change cos square theta. We know that cos square theta is equal to 1 plus cos 2 theta by 2. That is another relation. 1 plus cos 2 theta by 2 d theta. So this 2 and 2 cancels. So only 84 into 2. Now integrate. Integral of 1 is theta. Integral of cos 2 theta is sin 2 theta by 2 from the limit 0 to pi by 2. Now put the limits. 84 into 2. If we put upper limit, it is pi by 2 plus sin 2 into pi by 2 will give sin pi by 2. If we give lower limit, it will become 0. 0 minus sin 0 is also 0. Okay, no need to put. What is sin pi actually? Sin pi goes to 0. So we have only pi by 2. So that 2 and 2 cancels. So we'll get 84 pi as the answer. So the answer is 84 pi. That is by Gauss-divergence theorem we got the surface integral. Surface integral of the cylindrical portion is equal to 84 pi. So if you directly go for the surface integral, here you need to do 3 surface double integration separately. So it is better to use this Gauss-divergence theorem. By Gauss-divergence theorem, we will get the answer easily. Only the integration part is little bit lengthy. So for that you have to know this results. I think this you already studied in your school levels. Okay. So like this we can use Gauss-divergence theorem for finding the surface integral, and the Gauss-divergence theorem tells us the relation connecting double integration and triple integration, or surface integral and volume integration. So that's all for today. Thank you.